Today, we're going to talk about some lighting basics. We're going to kind of go over some basic terms and some general information and hopefully give you a little bit better idea of what we're doing optically. I'm kind of like the play-by-play guy, and then Dragon will be the color commentator. So when he's got something to add, he'll kind of pipe in and we'll go through all this. If you have any questions, raise your hand. We're going through a lot of topics, so it's probably best if you have a question to ask your question right away while we're on that subject before we move on to something else and then forget what we were saying. To start with, we're going to go over some vehicle lighting basics, terminology, and some basic concepts. And a little bit later, we'll go through regulatory bodies and laws and talk about some of that stuff. I'm sure you might have some questions during that time too, so ask away. And then I will go through some optics basics, talking about some just very general optical concepts and different types of optics that we commonly use. And then Brad Kay from the Advanced Engineering Group will come in and he will talk about LEDs. All right, so for the first section, we will talk about terminology, some units of measure, and then how we display light data to ourselves and to our customers. Oh, light, okay. So what is light? Light is really radiation that we can see with our eyes. So we've got a whole bunch of different types of radiation here, and that little narrow band in the center is basically what our sensor, our eyes, can see. And then we have the wavelengths of light from blue to red, but basically it's just some radiation that we happen to be able to see as humans. How do we measure light? So we're going to go through a couple different terms: luminous flux, luminous intensity, illuminance, and luminance. All of those words sound like the same thing, which makes it kind of confusing. So I've got some diagrams to go through and kind of show what the difference is. And we'll talk about the units of measure for each one, but they are very, very similar, and it's hard to keep them straight. So the first one we'll talk about is luminous flux. That is the total amount of energy radiated by a source. So over on the left side of the diagram there, we have a light bulb, and the luminous flux is the total amount of light that's radiated by that source, all of it all together. The unit of measure for that is lumens, which is a term you've all heard, I'm sure. So my next slide is about raw lumens and effective lumens and why we talk about it. So raw lumens is the output of a lamp based on LED datasheet values. And why we state that is because a lot of people don't have the equipment that we have. So we have a gyneometer, and we'll talk about that a little bit. We've got a whole system set up that we can accurately measure the output of our lamp. Some people don't have that, so they make a work lamp. They put 8 LEDs in there. For easy math, the LEDs produce 100 lumens, therefore their work lamp produces 800 lumens. Well, that's not really true because there's some other losses that are involved that are unaccounted for when you just take that datasheet value. If we do something similar and we accurately say our lamp produces 400 lumens, now it looks like their lamp has a higher output than ours, when really it could be exactly the same. So we differentiate and say raw lumens are the lumens from the source according to the data sheet.
I will just kind of comment from my end. I'm Dragan, you know all me for a lot of years. We are talking about the raw lumens in the sources. So, and he said the LEDs, but it doesn't have to be LED. So it's got to be, we have a lot of kind of sources from incandescent to halogen, to HID, to LED. The raw lumen is everything what is coming from a source. So basically, bulb, for example, let's say kind of age 11, it's around 1200 lumens, which is mean that filament which is kind of radiate around, and it's kind of like apple. That's the radiation, really kind of radiating all the way around. Okay, that's the raw lumen, and it has around 1200 lumens. When you take that bulb and put in the reflector, most of the people knows what is the reflector. Okay, you're getting really 30% efficiency. So basically for 1200 lumens, you're getting to 300 lumens. That's what your eyes see. Now there is a kind of marketing and your games, sales games, you know, saying, oh, my lamp has 1200 lumens. No, it's not. What your human eye is seeing is really kind of what is out of that kind of an optical system, and that's what is effective lumens. It's very kind of important to understand when you talk with your customer, because as Brian said, most of the people, oh, well, my lamp has kind of 4000 lumens. Really? Is it effective or is it raw? And, well, I don't have a clue. Then you measure and you see it's only 1000 lumens or less than that. So it's very important to have that kind of a distinct difference between the raw and effective.
So effective lumens are the real world output. So that's including all of our optical, electrical, and thermal losses in our lamp. So when we say effective lumens, that is the actual output that we get. I did put a link at the bottom. There is a kind of a explanatory blog post on our website that goes through raw and effective lumens and has some further details about that. So I just included that in here as well. So the next one from the left of the screen, after we talk about luminous flux, we go on to luminous intensity. So luminous intensity is the amount of light radiated in a given direction. So coming off that source, going in this direction, we're talking about intensity. So the intensity coming here might be different than the intensity going here. The unit that we talk about for intensity is candelas. It's also a term that we use often around here for our products.
One more comment kind of from a lumen intensity. We are optical guys and kind of, you know, a little bit more, it doesn't matter. So for us, this is very kind of common, but for you have to see pictorial, what does it mean? Luminous intensity candela, if I take kind of, you know, any lamp and I slice that lamp kind of, you know, so let's say this is the beam pattern which is going here from infinity because air doesn't have resistance. Let's take that, assume that there is no resistance, okay? So if I make a slice of this pattern and measure this point, okay, and slice, so there is a ray which is coming in infinity, and wherever I pick that point at that ray, intensity is the same. That's the candela, okay? We're gonna get to the lux, what is the lux? But that's the candela, that's the intensity. Intensity is the constant, just remember that. So wherever you kind of look at that, it's kind of directional kind of intensity of the light. It's not a light at that surface at this location. Does that make sense now?
So, question, on work lights, why are we using effective lumens, generally speaking, as a unit of measure, but in the headlight, we more often refer to candelas as being more relevant? What's the difference?
The difference is really where is that use, you know, of the light. So basically the working lights is kind of generic kind of overall floodlight. So most of the people kind of referring that to the lumens. How more lumens, more brighter, which is kind of in the basic, yes. For a headlamp, especially high beam, you really don't care so much about lumens as much as you care how far you can see. And far you can see is a really candela kind of, you know, measure. So for a headlamp, for a low beam, which is, it's a mix kind of, you know, things. For a low beam, we're using the lumens or lux. You know, for a high beam, it's more candela because it's directional versus really location in the surface what you can see.
Okay.
So before we kind of, you know, continue a little bit more, just basics, the source, again, kind of, you know, it's always kind of, I'm coming from a basic as a teacher and long time. It's, well, do you understand how even work? You know, let's say kind of, you know, filament source. How does it work? It's a pure mechanical interaction, really. When you take kind of, you know, like a kid, you take a rope, you know, and you take that rope and kind of, you know, make it that amplitude. What's happening with the end of the rope? It's going kind of, you know, up and down much more. Yeah? Everybody kind of try that. It's exactly what is happening with the filament bulb. They put a current, they kind of, you know, take this part of the rope and kind of end part of the rope and put a lot of current. So the rope will start to resist and go up and down, and so fast, then it kind of start to generate the heat. From that heat, start to generate the light. That's why that kind of, you know, source is only 5% efficient. all that kind of work and all that energy going just to kind of, energize that filament to emit it that light. HID, it's like two electrodes. So you got the two electrodes and they're kind of, sparking in between, and there is a gas, xenon. That's what they are calling a xenon lamp. It's just because the gas inside of that kind of, globe. So that spark kind of, spark that arc, and arc inside kind of, emitting the light. And that's what is the HID. LED, that's interesting thing. It's also somewhat mechanical things. So there is a chemistry, epi layer, which making electrons, okay? And now that electrons start to kind of go very fast. And there is another epi layer which has a holes, okay? This is all on the micro level, very tiny, tiny, tiny thing. So those electrons going very fast, hitting that holes, but there is so many electrons and so few holes, okay? So those electrons, and they're fighting. Who's going to come through the hole? And when it's coming through that hole, it's become photon. And that's what you see. That is why you're seeing the light. So these are the sources, how they are working.
So our next term is illuminance, and that is the amount of light on the surface. So now we've started with our source over there, emitting all that total light. There's light going in a direction. Now we're on the surface. So the light incident on the surface is measured in lux.
That's the distinguished difference. Again, directional kind of candela. So candela, remember, wherever we slice that, it's the same value. Now that candela or lumen, it's hitting surface. Okay, now we have a brightness of that surface, and that brightness, it's a square of the distance proportional. So if I take kind of the same amount, same beam, and I put that kind of my surface here, has X lux, okay? If I go like that, will be Y lux, which is much more less. So it's a square of the distance. That's the difference. Kind of, one is a square of the distance, one is a constant all the time. Candela lux. So when you go somewhere and someone tell you, well, I want a lamp to be 100 lux. Your immediate question is what?
How far away?
How far away? Thank you, Kyle. Because it doesn't matter anything to us. You had 100 lux. I don't know. What does that mean? Where is that kind of source located and how far away? That I can calculate distance and then I know what it is. And you know what it is.
And the last term we have to talk about here in this diagram is luminance, and that is the amount of light radiated by an apparent surface in a given direction. So this is one in our industries we don't use very often. Pretty much there's one case where we use it, and that is with license plate illuminators. So if you picture this system as a license plate, we have a lamp over here shining on a license plate, and what we're looking at is the amount of light coming off that license plate in a direction. I'm going to talk about one more term here that we use a lot is color temperature, which is talking about the color of a white light. So what I've got here is kind of a scale showing various whites with different color temperatures. The lower color temperature, starting down here, 2700 K, this is going to be more like a halogen bulb color temperature. And you'll see it's all white, but this is a little bit more on the yellow side. And as you move up, it's going to become more and more towards the blue. So this is about a halogen. Up here is about the HID sources. Our LEDs are in this range, but you can get things all throughout this curve here. When we look at color, and when we talk about LEDs, you'll see this chart again. You look at this CIE chart over here, and what you'll see is you go around the perimeter, there's numbers in the hundreds. That is the wavelength scale. So starting at the lower left bottom, where you're in the blue and the purple, it's 300, 450, 470. And as you go around, you'll go from blue all the way around to red. This black line here is where all the white falls, because what is white? White is all of those colors put together. And as you go along that curve, you get varying colors of white. So color temperature is kind of a one number definition of what that really is. On this chart, we can define what that is a little bit more because it's really two-dimensional.
All right, I got two questions, but I'll start with one, let you answer, and then I'll ask the
Sure.
second one. So the first one is the color temperature that you have. You can see from 27K up to 7,000K. Why is color temperature measured in Kelvin as it relates to that black body line?
That's a good question. I don't know the answer to that question.
No?
It's a unit what we use. I don't know really kind of where it's coming from.
Okay,
It's a unit kind of what you use.
it's okay. I believe it's actually the tungsten
tell
filament
us.
temperature. So tungsten filament, basically the black body line is black body radiation. All
Black body
metals-
locus, yes.
All metals, all gases, when you heat them up to temperature, they will radiate light. Like you said, it's a very inefficient way to do it,
Yeah.
incandescent. But those Kelvin measurements actually correspond to what temperature that metal would be at to emit light in that color. That's why you have red hot versus white hot. When you get white hot, it's a much higher Kelvin temperature. So
Yeah,
Thanks.
I'll ask the second question.
yeah.
Which is, so for those given color temperatures, we obviously use different LED manufacturers, and those LED manufacturers have bins that are associated with those colors. Have the LED manufacturers standardized yet those color bins?
Go ahead.
Yes and no. So as Kyle was saying, LED manufacturers produce an LED and they put them into groups due to different characteristics, one of which is color. They have varying colors of the same LED. So for a long time, everyone had their own color scheme. So this company had one way of doing it, this company had another way of doing it. How they would divide it up would be different. The size of their bins would be different. There was an attempt, or there has been an attempt to try to standardize that through ANSI. Many of the LED manufacturers that we use will bin them with ANSI bins, but not everybody. So therefore the answer is yes and no.
Yeah, the problem is how really LED coming, kind of, so they are going to grow that in a big accelerators, and there is a big wafer. So wafer, it's mean kind of 10,000 LEDs all together. And it's coming up like a big kind of, you put like a mushroom top. That's how it looks like, kind of, so, and then they take ceramic cutters and kind of other, or lasers to cut them in those small dies. As that kind of big round kind of, wafer of 10,000 or 100,000, it depends how big the LED is, there is a different illuminations because they are cutting that 1 millimeter by 1 millimeter from that big kind of, wafer. So that's kind of generate a different illumination of the LEDs, and they kind of put that into a bins. Now the human eye, especially white, can see difference only when it's 500 Kelvin difference. So plus minus 250 Kelvin of any nominal value. Nominal value would be, let's say, 4,000 kelvins. So that's what most of our customers are asking for, plus minus 250 kelvins. Guess what? That is a very tight tolerance, kind of, it's a lot of money. So what we are kind of working is a plus minus 500 kelvins. But if you take two lamps and you do for a low tolerance of minus 500 Kelvin and high tolerance for plus 500 Kelvin, you will see difference in the color temperature. It doesn't happen that much, but you will see. For example, new projects what we have with some customer, they demanding plus minus 250.
Especially DRL applications.
Yes, especially those kind of daily applications. DRL standing day running lamp, daytime running lamp, and it's kind of over day. So because it's working 10 hours, they don't want to see kind of 2 or 3 guys sitting kind of on a pump and so pumping their motorcycle, for example. They have a different appearance of that motorcycle. That's why they want that exactly that kind of tight tolerance. But the color, it's very it's very kind of, complicated thing. There is a lot of things what you do with the color. This is just white, but what color? What yellow, amber. So there is a 3 chromatic coordinates. How you calculate it, what is the red, it's really red, or amber, it's really amber. Then there is a CRI, color rendering index. How white really appear and how texture is the white. So with a certain color rendering index, kind of, there is what they're calling a dirty white. And ideally it's 100, and very bad it's a 50. Okay. What we are using, kind of, our kind of LEDs are around 5,000 Kelvin with CRI 80. So basically, it's really purity of that white. Like you take a pearl, and it's really white, and there is something a little bit yellowish, then it's more yellowish. Purity of that white, that's how they measure color rendering index. I don't want to go too much in details because it's getting kind of after that scientific. But when you talk with the customer, usually we are using 80, and we are using kind of binning plus minus 500 kelvins. Okay. Now the sunlight is right here. That's the bright sunny day. Okay. When you kind of go somewhere in a pool or swimming or whatever, Arizona, so 6,300 kelvins. That's the kind of good. Now, depend of the application, color temperature is very depend and very kind of important. If you are on a road, and if you are in that is a pavement, and that pavement is somewhat gray kind of color, and tarmac, whatever it is, LED it's a very nice source. But if you are in a kind of very yellow, surface, or very black surface, that because it's kind of, that color, temperature, and blue peaking in LED, you will not gonna see very well. In that case, it's better to have a lower color temperature. Basically, when we went to that kind of, in the Yuma ATV course, where is the sand, and when we put kind of, very bright LEDs with sunlight kind of color temperature, they perform less than LEDs in this kind of, color. So from all this what we are talking, you have to understand kind of, bright sun is here. We can do any type of this. Of course, if you take LED in this color, it's a little bit less efficiency, so cost will gonna go up. Okay, and you need to know what surface you wanna use that LED. So that we're going to kind of tell us in which way we should kind of choose LED and how to design the light.
I was just curious, I think you might have alluded to what would be my guess of the reason, but what changed from a technology standpoint from a manufacturing side perhaps, to reduce the cost of LEDs? Because LEDs, if I don't remember the exact year, I think 1960 have been around, something like that, but all of a sudden we've been able to utilize LEDs. What changed from a manufacturing cost standpoint to make them economically viable?
Well, LEDs kind of came by interesting from this country. It's a GE kind of get first LED in 1962. And what is interesting kind of information, after a certain period of years, 5-6 years, they somehow deemed that's not kind of so much prosper technology, so they sell all their patent. Very interesting.
Oh, it was only red, right?
Yeah, at that point it was only red. But what is really kind of, it's really mass production as anything. So efficiency of LED going more and more. So as they are kind of getting, improving, there is a certain things what they do in LED and improving every single year. What is interesting information, you can count every year for 5 to 10% LED we're going to go up, somewhere up to 2025. That's what is the prediction in this point of time. But really, all that kind of efficiency and really turning the heat into photons, that's the all kind of game in the research in this point of time. So pure heat inside of the LED, that kind of enable more and more as it is efficient, they kind of, putting more and more automatic lines, which is LED going kind of less and less down there. So efficiency and technology development turning heat to the photons is getting kind of this technology more and more affordable. Because now, instead of using 10 LEDs to meet one kind of specifications, you can use only one because it's that much efficient kind of from, let's say, the use of LEDs was 2000, I'm talking about white LEDs, will start to boom kind of immediately, and efficiency kind of went probably from 2000 to today more than triple. And they're still going to go up and up, which is mean reducing the LEDs, reducing your cost, it's much more affordable as well.
I pulled this from the JW Speaker website. Just wanted to point out under here, we show our raw lumen output, our effective lumen output, and our maximum candela, and our color temperature. So most of these terms that we just talked about, we do also publish on our website. So you may get questions about them because we're putting that information out there for everyone. So the next thing we're going to talk about is how we display light information from our lamps. And we pretty much do that with two different types of diagrams, isocandela diagrams and bird's eye diagrams. So the first one is an isocandela diagram. And what this really is the light output in an angular space. So we have a picture of the light is in the center of a giant ball. So we've got our light in the center and it's shining on the inside surface of this giant ball. That's what this really is. So this shows plus minus 60, that's 60 degrees. So this is all an angle space. So it goes 60 degrees up and down, 60 degrees left and right. And it's kind of shining on the inside of that ball. It is similar for what we talk about and for our lamps and the size of our lamps. It's similar to shining it on a wall. So this is kind of like the picture you would see on the wall, but it's really the inside of a sphere. And then what this diagram shows, you see all these lines with varying colors. This is the candela lines. So as you go up here, there's a scale at the bottom that shows the luminous intensity values. And as you go from, in this scale, blue to red, you're going to go from low intensity to high intensity. So in this lamp, this center area is going to be much brighter than the area out here.
Isocandela diagrams, so again, kind of you guys, you're salespeople, you're talking with many, some of them educated customers, some of them are not. So always try to kind of, get that pictorial way to explain what is the isocandela diagram. He said it's really kind of, lamp in a sphere, which is kind of, a certain distance. And when you start to talk with some customer, well, yeah, same to you. So they might not understand what you're really saying. Kind of very nice analogy. It's kind of, well, take the lamp, just shine on garage door. That's what is isocandela diagram. Oh, I got it. So it's a very simple explanation what it is. And it's very complicated from your perspective and our perspective. When we see this, we know exactly how lamp perform. Most of the people, 99%, will not gonna know. So you gotta guide them somehow through that. What does it mean? And to guide them, there is a 5 major factor what you have to kind of remember. Okay, in isocandela diagram, the number 1, it's a punch. That is the terminology and everybody kind of using everywhere. It's really reach down on the road, wherever it is, field, whatever, truck, trail, whatever, okay? What does that mean? That is this most intense of the lamp, okay? That's the number 1, punch. Number 2, it's a spread, okay? So most of the kind of, our working lamps are characterized plus minus what, 30 degrees or whatever. That is mean kind of how much they're wide pattern. So that is the spread, okay? Number 3, it's overall brightness. Brightness mean kind of, I can have all these kind of parameters fine, but it's kind of have lumens very low. Okay, that's brightness lumens. That's what they're kind of, connected. Okay? So number 4, it's uniformity. So basically, when you look at this diagram for some kind of, our competition, and you see some streaks, that is mean when you put that down on the road, we're going to be some streaks. We're not going to be pleased for eye. Usually, when you ride that kind of, we're going to, vibrate, and you're going to see that kind of, playing in front of your eyes. Okay? And kind of, number 5, it's intensity overall. Okay? I'm sorry, intensity, foreground. Foreground is mean how wide vertically your pattern is. This is a very kind of important wear to motorcycles, ATVs, because you're open and you don't want to see that your light starting 5 meters in front of your vehicle. So what the rest of that? So basically that is the foreground light, and it's usually kind of getting around -20. That's the number, which is good. But so 5 major parameters. So when you talk kind of with a customer, ask them what they want in those kind of 5 major parameters. They might tell you, well, I don't know, but this is my benchmark. As soon as you have a benchmark, you ask, okay, please authorize that or give me information about those 5 major parameters.
One more aspect on this diagram, it might be kind of small here, but at least in this particular format, we have our lumen value. So that is the total amount of lumens produced by this lamp in this window. And as a standard speaker, we use the ± 60 by 60 window. For all of our lamps, some of our really wide lamps, we might have to measure a little bit wider, but 60 by 60 window is our standard.
This is interesting information for you guys, a little bit advanced, because you can play the games here again. So you have a source which radiated kind of certain pattern. Okay. Let me see if I have. Do we have any? Yeah. Thank you. So let's say kind of here. I have a pattern of the working lamp. Okay. Okay, and that working lamp has, just for a number, 1,000 lumens. Okay? I can choose the window where I'm going to look at it. That is this 60 degrees. So if I choose the window, let's say 30 by 30, that we're going to have, for example, 500 lumens. Okay? If I choose this window, which is 90 by 90, that's going to have this 1,000 lumens. So basically, it's very important to define what is the window when you're looking your pattern. Okay? So basically, this number for this kind of isocandela, which is around, what it is, 1,000 lumens, is it? Around 1,000 lumens. If I would chop that window and show only this to this and this to this, that would be a 500 lumens. And both information are correct. So I can say my lamp performed 500 lumens or my lamp performed 1,000 lumens. It depends how big the window is. Okay? It's good information for you to know when you look at some other competitor kind of, isocandela diagrams. How big the window is, what they're looking for. Go ahead.
I've heard the terminology of a light having a hot spot. So can you explain what that is, and is that coming from the source, and is it a bad thing?
Hotspot, well, now I would need kind of in what context, so you heard that hotspot. But let's say in this kind of, context, hotspot will be equal to the punch.
Is
Okay.
it a bad thing?
No, it's a good thing. Well, it depends how big it is. How much candela you have in your kind of hotspot. And what is the application? That's the whole kind of, game. If it is, I don't know, if it is a low beam, you would like to have that 15,000 candela or 20,000 candela in that window. If it is a high beam, you would like to have that 60, 70,000 candela in this small kind of, things. Okay? If it is a working lamp, depends how big the working lamps, but usually it doesn't matter hotspot. Hotspot in a working lamp, it's not a good thing. In a working lamp, you want to make kind of, everything very uniform, very spreaded, and you don't want to have a hotspot because working lamp, it's what? You work when you use that lamp, okay? And if you have a hotspot in front of you, your eye will be drawn, like it or not, to that hotspot. You're working always looking that hotspot. You don't want that hotspot in your working lamp. So it depends what application it is. So it mainly is a good thing. I believe that people refer when they say hotspot to the punch of the lamp. Okay? Go ahead.
I'm just wondering, is there a standardized window that like we use and that competitors also use, or is it just whatever you decide?
There is no standardized window per government or per regulation. Whatever we design, we at JW Speaker, we want to be really somewhat real and honest, kind of what we said. So we pick this plus minus 60 degrees because we think in that window will be all kind of light. When you are sitting in any kind of vehicle, your peripheral vision is 120 degrees. So basically, when I'm looking at that, I see 60 degrees here. Okay? So peripheral vision, it's around 120. That's the reason why it's plus minus 60. So everything when you sit, that's what you see. And that's why we are using that window.
And like I said,
question.
Most of the time, all the lamps that we make and the lamps that we look at, the full pattern fits within that window. It's not like we're chopping off some of the main pattern and then we're not getting an accurate measurement. Most of the time, it is completely within that window.
Yeah. That window, that peripheral vision, it's important. Well, this is how we kind of working, but there is certain things what you do for safety kind of lamps, like a strobe or something, So most of the situations you will gonna look at somewhere else, but strobe will gonna be somewhere here. But you're still seeing. You don't look at it. Your peripheral vision kind of, start to see something, it's kind of doing like that, and then you take your attention. Okay?
So, in a sense, after we've looked at the pattern on the wall, then we want to look at the pattern on the road. Most of what we do is lighting up the area around our vehicle. So this is a bird's eye diagram. And what this shows in this case is a vehicle over on the left side, pointed toward the right. And what we're looking at is that light hitting the road. This is the surface of the road, and all of those diagrams there are now showing lux values, as we're looking at the light on the surface of the road. So now our scales on both sides are going to be in distance. In this case, this is in meters. Meters is what we usually use. And because it's lux, and as we talked about before, the distance for lux calculation makes a difference. So when we create these diagrams, this is when we need to know where are the lamps mounted. So if they're mounted here versus here, we're going to get a different picture because the lux values will be different.
Again, it's lux. We said that kind of brightness of the surface from a source. So that's the kind of, first what you're asking as well. If your customer asks, well, I need a bird's eye. It's just kind of looking something like that, kind of, we can look at that for any height we want. That's kind of something what is in the software. So we can kind of, give that picture however you want. But you have to know where is that lamp installed, especially for functions like near field illumination. What would be the near field? Kind of, working lamps, low beams, that type of illumination. Because it's very important to know where is the source to give you kind of an accurate picture how that looks like. Okay? For very kind of intense lamps like spot, high beam, kind of modify high beam, it's not that much important because it's going that much kind of, far away. So you're going to see that needle anyhow. We'll probably have that kind of, here.
I might, yeah.
Yeah, okay. So that's kind of, again, for bird's eye, it's kind of, where is the location? to understand, kind of to give you accurate picture. Okay? Go ahead, Kurt.
And I understand it would be different based off of application, but with all the confusion with lumens, why is there not like a something that does like weighted averages and combines lumen, candela, and lux into like a more usable number that would be universal across headlights? Does that
Okay.
make sense?
Well, any question is a good question. So, but you take kind of, so orange, apples, and pears and put everything in one basket and say kind of, oh, let's go make juice. You know? So it doesn't work like that kind of, there is a different unit for a different applications, so, and that's what we have to use. So lux is brightness of this surface by this source at that distance. And you cannot use candela in this kind of case. It doesn't exist such a unit. So it's a lumen per square meter. That's the lux. So they take some of those and kind of make that, and derivative of that is the lux. Okay. There is also North American kind of unit, which is a foot candela. But most of the people and everybody else kind of using the lux. Usually a ratio between low beam and a high beam, it's Holy Trinity, 1 to 3. Okay, so good low beam, it's around 100 meters. Good high beam, it's 300 meters. Reach down on the road. Steve.
Another term that's used a lot, particularly in the United States, is candle power.
Oh,
7 million
Very
candle power,
nice.
12 million candle power. Could you briefly address that? And from a sales perspective, how should we treat that?
Yeah, that's a very kind of, so good question, because people abuse all those kind of units, and kind of, as you see probably in the past, you see the lamp which is 5 million candle power. I mean, there is no way that something can be 5 million candle power. First, the candle power and candela is the same unit. It's absolutely the same unit. But somehow, down on the road, people come up with the candle power as candela in a certain area, average all together, and spit up the number. That's the candle power for some lamps. That's how they come up with the 6 million kind of, candle power. So basically, they have that kind of go back, okay? They have this isocandela diagram, okay? They average that, let's say, at 0.1 degree, a small, can you imagine the small kind of squares here? As you can see, can you see the squares here, very small? If I would take mathematically and average them, sum them, every candela in every single one of those squares, that's my candle power. Do I lie? No. Does that mean? Nothing. But it's a good marketing tool. Oh, my lamp is 5 million candle power. Oh my God, it's got to be something like sun bright. It's basically, that's what they do. That's the candle power. Hopefully, and kind of what we are seeing, that unit is kind of dying, and nobody using that anymore, because it's really, people start to realize that doesn't mean anything. Really, it doesn't give you anything. Okay?
I'll go through this pretty quickly here. I just kind of wanted to show that what you'll commonly see from us are isocandelas and bird's eyes that look like the examples I showed here. But this is how it looks like using the softwares that we use. And it can look very different. We can make it look all sorts of different ways. So I just have some examples of different things that are all isocandela plots. They might look a little bit different though. So in this case, this is, I think, similar to what I showed the first time. We've got a varying scale. It kind of varies from blue to red in gradual tones. We could look at it with just colored lines to indicate what those different values are. We can look at it with just blocks of color, so anything above a certain value is just a solid color, and we can kind of show it that way. This is also an isocandela plot. This is actually an example from our goniometer. If we do a test and print out the results, this is what you would see. So they all look a little different, but most of the information it's the same type of information. It's displaying it just in a different way. For bird's eye diagrams, we have the same type of thing. This is kind of the gradual color scale. We can look at it more in a block diagram. This is actually what we use as the basis for the bird's eye diagrams that we use on our marketing information. And then something from the goniometer as well. Okay, so now it's audience participation time. I've got 2 lamps here from the Model 523. Which one has more lumens?
Same one.
That is correct. This is the same lamp, exactly the same lamp. We're just looking at different window sizes. So on this side, we've got a window that is plus minus 80, 80 by 80. On this side, it is plus minus 40. The intensity is exactly, the maximum intensity is exactly the same because it is the same diagram. The lumens are different because we're looking at a smaller window here. But if you don't look at the scale, well, it looks like this has a great big hotspot and that one is much smaller. So this is the way that we can kind of make it look however you want, but that's what you got to pay attention to. What are you really seeing? What is the window? What is it showing?
That's exactly the same sketch here, kind of now in exactly the sample. The same lamp, you got kind of 3,000 lumens versus 2,700 lumens. 3,100, whatever. It just depends. And if we would open that kind of all the way up to 90 degrees, that would be at 3,500 lumens.
So the next section is talking about light pattern characteristics. Dragan talked about this a little bit already. So what I've got here,
Before he starts to kind of explain what it is, again, kind of isocandela diagrams and bird's eye diagrams are really for us optical geeks. You know, so we see that, we can, okay, I see this and streaking, whatever it is, analyzing. Most of the people start to kind of, you know, asking, is there any better way how you can display the pattern of the lamp that I can understand as a kind of normal average user? And then kind of we had to come up with a different software and different way what your human eye as isotropic kind of function seeing on the road versus those beautiful colors, beautiful lines, beautiful whatever it is. So, and that's what is coming up to those type of the diagrams. Now he's going to explain what they are.
so as Dre said, this is a shot from our virtual reality software, which does help try to explain more easily what the pattern is going to look like. So in this case, we've got a motorcycle down here at the bottom of the screen and shining down the road. We've got the light pattern here. And I'll go through these characteristics here. So as we talked about earlier, the spread. So that's looking at how wide does the pattern reach all the way across the road. We've got the punch or the hotspot. How far does it go down the road? How far can you see with that? We've got the foreground that shows the light that's right in front of the vehicle. See, for something like a motorcycle, if you don't have any body panels or anything right in front of you, you can see right in front of you. So you want to be able to see what does that light look like there? Do we have any streaks or anything like that? And then the other things, the overall uniformity of the pattern. Again, are there streaks or are there dark spots? We want to have a nice uniform distribution of the pattern. And then the overall brightness of the lamp. I have an isocandela plot here, which I think we used to go over the same terms, but Dragan kind of did that already. We've got the overall spread, the punch, the foreground light here, and then the uniformity and the brightness. In this case, you can see this from the bird's eye diagram as well. So the bird's eye diagram, the vehicle's over there on the left, pointing to the right. So you can see the overall spread of the pattern. You can see the punch here, how far it goes down the road, and the foreground light, that would be right in front. And then the overall uniformity of the pattern. You can see here, this is minor, but there's a little bit of a streak starting here as the lines start to curve. This might be a little bit of a dark spot in that area. And then the overall brightness doesn't really show up in the bird's eye diagram, I would say.
It doesn't show up.
So when looking at that diagram, because it's measured in distance, both from left to right and then from the vehicle on outward, when I look at that, it looks as if the pattern actually is skewing slightly to the right. It's not perfectly centered down the road. Can you explain why we would design a light that would skew slightly to the right?
This is a automotive type pattern, which is asymmetrical, meaning it is not symmetrical from the left side to the right side. If I go back to this diagram here, so this is the isocandela diagram of the same lamp. You can see this hot spot is just a little bit off to the right side of the road, or the right side of the vertical horizon there. So you also see there's a little bit of a elbow right here, the lights goes up. So in this case, this is a automotive lamp like we would drive here in the United States. We keep the left side cut off low so that you're not glaring oncoming traffic that would be coming on your left. And you get a little bit more light on the right side to see down the road and to see the road signs that are there. So this is a little bit on the right side, and we go to the next slide. In the bird's eye, you can see that this is skewed more towards the right.
Everything is kind of connected to the safety. So there is two types of the very different vehicles, what we are talking about here. It's a motorcycle versus car. So the car has two light sources which are on very kind of distant separation, and it's much faster on the road at least than motorcycle. Okay, so basically, if that is the case, that vehicle should be kind of, you should see when you are in that vehicle more on the right side where are pedestrians, where are kind of, deers or any obstacles which might come at you at that speed. That's the reason why kind of, that pattern has to be asymmetric. So it's more kind of on one side of the road. Of course, in England or any other kind of guys, that's another side of the road. But that's the reason, safety. Why is that? Motorcycle has a one lamp. There is a motorcycle with the two lamps, but they're still very much combined. So there is no that separation, okay? So they don't have a choice. And they're kind of, asking more for symmetrical pattern because it's only one light source. And the speeds are more kind of less, so I prefer to see more symmetrically left and right than only from a right side, because I'm not protected. In a car, you are protected somehow.
So Brian, if you go back to that prior slide, show us where is the chevron in that view, and why is it called that?
That is this little elbow that's right here. We call it the chevron. There's multiple terms for it. The kink, elbow. Anything else I'm missing?
So that's excellent question, Mike. But immediately here, probably there is a people which, what do you even ask? What is the chevron? And then he said the elbow. Then it's a kink. What the hell it is? So first, okay, so basically, if we have here again, let's say, and this is age represent horizon. So basically, you're seeing that. Now I'm going to put it very here. As the road in perspective. Okay? So basically, you want to illuminate this kind of portion of the light more than this portion of the light when you're in the car. So basically, you have something which is this kind of pattern. This geometry of this line, which is going kind of, tracking horizon, and it's above horizon, but there is nothing here to make a glare, that small L profile, that's what we are calling, or its terminology, it's chevron, kink, elbow, whatever you say. So there is a different terminologies for that part of the light. So basically, you can have a car from this side. They are in a glare. This is a glare. This is the dark zone, protected, and this is the light zone. And you want to see here if it is a cyan or some kind of small pedestrian or whatever it is. That's why you kind of put more light on the right side of the road. That geometry, that is the kink or chevron or elbow. And that's why we need that to illuminate it one side of the road more than another.
And that's prescribed by DOT, right? That particular pattern?
That particular pattern is described by DOT and by ECE, more in ECE, meaning kind of European regulations. But they are similar, not the same, similar. But it is required by DOT or MVSS. MVSS standing for Motor Vehicle Safety Standards. Okay? And they require this kind of illumination.
Just as an example, I have up here what is a terrible pattern. Realistically, there was probably something very wrong with this lamp that it looks so bad. But this is a good example to show some of the streakiness or some of the things that we look for in the pattern.
So one of our customer coming to us before they switch the whole business with somebody else to us. This is one of our competition lamp. So what they made, it's really terrible. I'm not going to say the name. It's kind of, that's all out of it. But that's their kind of, pattern. And now, continue, please.
So when we look at this, first of all, I mean, it looks funny. There's lots of different colors here. We've got red, and then we go to the yellows, and then we go back to the reds. So there's a lot of color changes. There's these finger-like elements here. There's something here where you even go into the green. So when we see something like that, we know, okay, there's going to be some streaks and some really, it's not going to be a uniform pattern. So that's kind of looking at this from the isocandela view. When we go into the bird's eye view, now you can see here, again, we've got some yellow areas with some green right next to the red. So it's going to be very bright, very dark, and then bright again. You can see kind of these, when the lines come back and go forward, that's going to be a streak as well. So you can see a lot of that in this pattern here. And then I also have a grayscale version of it, so you can kind of see more what it would look like with the white light, and you can more clearly see there's dark spots and bright spots. So this is the type of thing we look for, not to this extreme, but this is a good example for it. But these are the more subtle things that we want to look for and make sure that we don't have streaks or light spots or dark spots in our pattern when we're evaluating them.
Brian, you might have been going with this direction anyways, but can you elaborate a little bit more from the human interface perspective on that? I think that there'd be value in opening the conversation of why does this matter? Elaborating past that, it's just not as pretty looking. What is the human interface? Why would our customers care about, quality of light and cleanness and not having it disjointed like this visual displays?
Sure. I think one of the first things is something that Dragan mentioned earlier. When you have a bright spot in the pattern, that's where your eye is going to be drawn. So if you're driving a car and there's a bright spot right in front of you, you're going to look here and you're not going to be looking down the road, and that's going to be unsafe. If there's a bright streak off to the side, maybe as you go past some tree-lined areas or something like that, all of a sudden that's going to catch your eye, and then you're going to look over here when you're driving this way. So when you have streaks or dark spots in the pattern, it becomes distracting, and you start looking at those areas.
That's it. It's safety perspective. So as a human eyes, I kind of, you're consciously or subconsciously looking wherever is the bright spot. If that is the carpet of the light, you're just looking normally as you're kind of behaving every day. But if there is a bright spots and streaks, your eye kind of subconsciously we're going to start to follow those things. And that it might be in front of the car, as he said, might be kind of left, right of the car, or any vehicle, and you don't really pay attention where you go down on the road. So basically, any pattern has to be made in that way that your eye is drawn to the purpose of that pattern. If it is a low beam, it's going to be very uniform, very carpet of the light in front of your car that you see. If it is a high beam, you want even to reduce that kind of light when you're switching to the high beam. Now that from this, you go that kind of shift in your eye that you're looking down on the road. Because you're at the speeds, say 70, 80 kind of miles per hour, when your reaction and kind of braking time, it's required maybe 20, 30, 40 meters. And if you're done looking at that point, that's the safety compromise. That's why you don't want those streaks that your eye is drawn and your concentration, what they're calling distraction during the drive, it's kind of completely.
Thank you, everyone, for coming back for laws and regulations. Yeah, this is the fun part. This picture's accurate. There's a lot of them that we deal with. It seems like everyone has their own thing, and that's why we've got a lot to go through here. So what I'm going to do is basically talk about the different regions of the world that we deal with and the organizations, regulatory organizations that are in those areas, mainly so that you're familiar with what all these initials mean and who they are and what we do with them to certify our lights. Okay.
One more comment, kind of, it's interesting to know, but I believe kind of that we are dealing with one of the most complicated products on a vehicle. People doesn't understand that. Most of the people perceive that, oh, yeah, I have a plastic and bulb put together, I'm done, go. So, but it's very hard. There is two major components. The one component is regulatory. So all our lights has to meet something. It's not like you're making a chassis or you're making a kind of, rims, or there is no regulations for those things. There is internal things in the company what they make that product better, but there is no government overseas. Government oversees kind of, so suspensions, steering wheels, brakes, lighting, and some other things. And on a safety scale, the lighting is second. The first is suspension, the lighting is second, the brake is third, steering wheel fourth. Which is interesting. People would say, well, of course, steering is the first. No, we are kind of working our way up, kind of, how much safety is. If you don't see, you're going to crash. There is no kind of, doubt about that. So one component is regulatory. The second component is really that styling, because again, it's not chassis, it's not kind of, even let's say brake, they have that regulatory component, but who cares how does it look like? Because it's all hidden. It's all exposed. So we have that kind of, aesthetic component and the regulatory component. We're going to talk about this regulatory component now.
So, starting in the United States, the first one you mentioned earlier, FMVSS, the Federal Motor Vehicle Safety Standard, particularly FMVSS 108. This is the document, the law that governs vehicular lighting in the United States. It is governed by NHTSA, National Highway Traffic Safety Administration, and as I said, it is the law, so there is no question about it. This is what we need to meet when our lights are on a vehicle on the road. It doesn't get updated very often.
So this is the major kind of things here for this country, FMVSS. And usually what you're going to kind of hear is FMVSS 108. 108 is just a number of that document which regulated the lighting. Okay? So for us, and that is regulated for vehicles on the road. Okay? There is a MVSS 405, is it? Which is low-speed vehicles.
500.
500, yes, thank you. MVSS 500, which is regulated low-speed vehicles. It's a different kind of MVSS, but it's good to understand. There is vehicles on the road and low-speed vehicles. Everything else, MVSS doesn't care. Okay? It's not regulated, right? And then there is a younger brother or reflection or whatever, which is CMVSS. C standing for Canada Motor Vehicle Safety Standards. It's basically just exactly the same as United States. Okay? But Canada accepting a both meaning a European standards and kind of, MVSS standards or US standards.
Since this has come up recently, is DOT approved a real thing? And when our competitors say their lamp is DOT approved, is that real?
That's an excellent question, which is right here. So yes, DOT I didn't have on the slide, but DOT is Department of Transportation. It's all the same thing. So when we have a lamp that meets FMVSS 108, the mark we put on it is DOT. That's specified in the document. So how are our lamps certified to this? It is self-certification through internal testing. So we take our lamp, we photometrically test it here, it passes the test, we put DOT on it, and we say we are certified. The government does not do any certification. It is on us. So what happens is if there would be some very bad incident where there was an accident and it was caused by a faulty lamp, the government is going to come back to us because we said our lamp was okay, and they will come and deal with us directly.
There's a small information that you should know. DOT, when it says any lamp which is on the road, vehicle has to be DOT. So that letter DOT has to be somewhere on that lamp, and that somewhere is the lens. That's what regulation is saying. It's got to be on a lens. But people today, government doing a little bit those kind of things. They're putting on a bezel inside of the lamp and those kind of things. But by the letter of the law, has to be on a lens. What I meant to say, all kind of domestic company, we are self-regulated. So he explained that. We do the lamp, we design the lamp, we measure the lamp, we storage that data, photometry, all points, that isocandela diagrams, we put in a certain directory. For any case, if NHTSA come on your door and tup tup, I want to see this, this is it, this is how it's through our system. But, for example, how foreign companies doing that, they are not accepted as a self-certified companies. So they have to have certification by a lab in the United States who has that kind of permission to do. There's only 2 labs to do that. The one is in New York, the one is in California. Okay, so all those kind of guys from China or whatever, they somehow have to pass through those things. If they didn't, then it's not legal lamp, even if they put the DOT there.
With the certification, what's included with that? What kind of testing is done then? Are there certain standards for every light that we put through this?
Yes, there are. The document specifies definitely photometric testing, but there are also environmental testing, various tests that we have to do to be compliant to this. And it does depend on what type of lamp it is and what it's doing. But yeah, so it's a mechanical test and photometric tests.
Yeah, certification test has like a booklet. Okay, there is a photometry testing which is performance on the road, and there is also environmental testing, which kind of include vibration, salt chamber, humidity, high temperature. All that you have to pass, put in some kind of document, and that is the document which is going with the lamp. Now, which lamp you do? Again, MVSS is really pay attention what they kind of do on the road. For example, there is a certain, they don't care about working lamps. Well, let me put it that way. They don't care about even fog lamps. Fog lamps are not kind of MVSS regulated. They are SAE regulated, but not MVSS. That's a distinct difference. MVSS is a government. SAE is recommended practice. You don't have to have your lamp kind of, passing SAE. Everybody want it because it's kind of, better, but you don't have to. That is Society of American Engineers, and they have recommended practice. And their recommended practice saying the lamp should pass that. I don't have to follow that. That's not the law. Is that clear? Okay, please, second question.
Are you going to explain the difference between ECE and DOT? And the testing that happens with that?
Yep.
Okay.
So the next one, SAE, Society of Automotive Engineers. So they set and oversee standards for automotive and other related industries. And it is a industry-approved recommended practice. So SAE is really an organization of people in this industry making best practice recommendations for all of these type of activities.
For your information, kind of just to know, when you have particular question on everything by SAE or regulation or whatever, Brian is sponsor for J584, which is a motorcycle headlamp. He's just getting kind of into SAE world as our representative. I am in that world the last 15, 20 years. I'm a chairman for recreational vehicles, chairman for motorcycle lighting committee, member kind of, with many other kind of, SAE standards and task forces, and also member of GTB for ECE regulations. So any particular questions, you can kind of find me anytime.
FMVSS 108, the law, is really based off of SAE standards. The issue is it was just based off of SAE standards from a long time ago. Because like I said, the law does not change very often. The words LED aren't in FMVSS 108 anywhere because they don't update it. And there's some issues that we have to deal with for that. SAE is a much more active organization, so the SAE standards get updated much more often, but FMVSS 108 is still the law. Again, for SAE standards, we are self-certified, so we do our testing here, and we mark the lamps, and we say that they are meeting the specifications. There's one more in North America I'll touch on here for the agricultural market. It is ASABE, the American Society of Agricultural and Biological Engineers. They have a couple of standards that are directly or related to some of the stuff we do. They have a installation standard, which is ASAE 279 dot. The XX there is for revision level. I think currently it is 17. That changes every time they update the document. And that document states what lamps are necessary for a agricultural vehicle, tractors. They mainly refer to SAE standards, but they do have a unique headlight standard specifically for ASABE.
So for agricultural kind of forestry and that, there is a different standards. It's not SAE, it's ASAB. So which is for that one, that's all what you need to know. These are the all kind of, different world, guys. Kind of, you step in SAE, it's huge like that. You step in that another, it's huge kind of, they crossing somewhat and referring to each other, but you gotta know every single kind of time which one it is. So they are different. You just need to kind of, when you talk with a customer, define what they want. Sometimes customer doesn't know, then we have to kind of, see what vehicle it is and then define for them. It's kind of interactive process.
All right, so now we'll go over to Europe. So next one is ECE, the United Nations Economic Commission for Europe, or UNECE. These are laws in Europe for automotive and motorcycles and agricultural vehicles that go on the road. And a lot of the ECE regulations are not only used just in Europe, but are adopted to many countries all around the world. How are our lamps certified for ECE? Well, first we got a fancy word there called homologated or homologation. This just means that we're certifying our lamps. So big fancy word that kind of relates to ECE, homologation. Only countries who are in ECE, in the union, can certify the lamps are okay. So the United States is not part of this, and therefore we need to hire a company that is part of that to certify our lamps, and we happen to hire a company called VCA, which is based in England, and they do our certifications.
With England's departure from the EU, will we have to get a new certification country?
That's a good question, and currently, not quite sure how that's going to work.
No, I mean, from my perspective, this is the Europe. This is not united Europe. And UK, it's a part of the Europe still, so this will gonna be, there will be kind of, part of the EC regulations. United Europe has their own regulations, which is, if you saw in some lamps that lower case is E. That is, so there is upper cases, which is Europe, and there is a lower cases, which is United Europe. What they wanted to protect the market, from any other guys. So you have to kind of homologate by Europe and then by United Europe to put a small E there. That's dying. That doesn't exist anymore. So it's only one European regulations. And UK is still in Europe, so they are not part of United Europe, but will be part of the Europe, so the same homologation apply.
Yeah, and ultimately, it probably won't be anything for us that's different. I'm sure on their end, there's some agreements that they'll have to do or something. But ultimately, in the end, it probably won't make much difference to us for the certification process and who we work with that way.
When we say Europe, guys, this is a whole world. It's kind of, follow the Europe. In some sense, kind of, what is the major difference that MVSS really address anything if it is really back up with the safety data. What does that mean? Let's say kind of, this type of the lighting kind of a report in the last kind of this technology of whatever, 5 years, that many crash accidents connected to that part of technology. Therefore, let's go kind of, regulate it. If they don't have that, they will not touch it. Europe is proactive. It's saying kind of there is a new technology, we have to do the new regulations for new technology. So that kind of starting to do last 25 to 30 years. So basically the regulations are like, now this is the Europe and this is our MVSS regulations. Now the whole world start to kind of follow the Europe. Now Australia, it's a part of that. Japan, it's New Zealand. Everybody, it's ECE regulated in this point, or 40 ECE regulations. We are only one isolated island as far as regulations, us and Canada. Canada has to because we're too strong, so gotta follow us. But that's what it is. We are isolated here, and there is all world which is follow ECE regulations.
So when we want to get our lamp approved for ECE, we have to bring in that company, VCA, so we can do our testing here. However, they have to come and witness our testing being done. So they come here, they witness our testing. After all of our testing is done, they issue a report that says that our lamp is approved and this is the approval number.
So, talking about FMVSS, we talked about there's the photometry as well as some environmental or mechanical regulations. Does ECE also have any sort of environmental regulations, and do those also need to be witnessed by the testing agency, or is it just the photometry?
There is some limited, I would say, environmental testing that we have to do. A lot of it's dealing with the type of material we use. So we do have to do some basically deterioration tests on the lenses. But it's mainly photometry.
Yeah. The major differences in ECE is they care of performance of the lamp, and the lamp to meet all kind of lighting regulations due to some conditions, if I have to put on some way, and that's how they connect the test. Those conditions is, are you meeting your kind of our points if your lens is dirty? Okay, then you have to perform, therefore thus you have to perform dirty test of that lens. Or kind of, if you have your headlamp working the whole day in Arizona sun, okay, it's wire on that way that's working all day, is your material holding that temperature not to deform and kind of, make a pattern all, so in others. So therefore you perform that heat test. And that's only what you do. But all those tests are connected to the photometry performance. Doesn't have to any environmental vibration, humidity, they don't care for that.
Yeah, and that's a good point. So when we have our homologation agency here and we're doing testing, we do a photometry test, but then we have to do multiple other tests with photometry afterwards to do all the testing that's required. So usually if we do a headlamp, we have to test 2 samples. It's 2 days of testing here that we have to spend to go through and do all the tests that are required. Canada, Dragan had mentioned this, CMVS 108. It is basically a copy of the FMVSS 108 standard with some minor changes for their own things. There's also a CMVSS 108.1 that includes some of the ECE standards, so they do take both. In China, there are CCC standards. These are very similar to ECE regulations, but they have written their own thing, so it's their own documents, and there are some differences, but for the most part, the photometric testing, the photometric points are very similar.
What is interesting to say, well, basically, they're taking the ECE and they're kind of rewrite that in their own language. Just kind of taking, ECE has a different, for different lamp, there is a different regulation. They take that all combined in one document. It's exactly the same lingo. It's just kind of, one document. And doing that, they protect their market, so it's a very expensive. What you need to understand kind of from that, when you do something and the customer requires CCC kind of, certification, it's usually per lamp $15,000 to $20,000 just to certify the lamp, okay? And it's mainly about money. It's mainly about investment, kind of, what they want to charge you for that. So you have 5 lamps to certify in a hurry, you're $100,000 bill. So you gotta kind of think about those things when you talk with the customer. If they want to CC, well, you probably have to pay kind of, for that.
As Dragan said, how do we certify it? We send lamps and money, and then a while later we get our certificate.
It is really like kind of, you're putting in a grinder, so you put something, send over there, you never see that ever, you get certificate, all good. Now we are taping, but it doesn't matter. We have one kind of, it was interesting because it cost too much money, really too much money. And they're saying, they're claiming we are measuring, we do this, we do that, kind of everything. So we purposely send the one lamp which failed. We know it's failed. Here it is, $17,000, 1 week later, boop, certificate come here. You're good to go. Thank you.
Wow.
So that's what is really happening. So it is what it is.
In some applications that we have where we don't have a whole lot of volume, obviously that's a very, very expensive certification. Are there any limits as far as a volume level that you need in order to hit, in order to require that certification, or for lower volume applications, do they have any sort of alternative process?
Great question, really great question. Yes, there is, different countries has different volumes. For China, as we know, it's around 300 cars, 300 vehicles. If it is less than 300 vehicles, they will grant you ECE homologation and accept that. If it is more, you have to pass through the CCC kind of, things. Okay, that's also applied to the Europe. I think Europe is 250. If you we did it something for Polaris, one of our companies' motorcycle in the past, and it is, I think so, 250 vehicles. If it is less, you don't need to even ECE homologate it as far as your MVSS approved. They will accept it for such a small contingent of the vehicle.
Next one, we've done some business with Taiwan. They also have their own specifications, however, they follow the ECE requirements. Our speaker facility has been approved by Taiwan for testing. So we had some representatives come here, go through our factory, go through our labs, and certify our facility for that. So with witnessing from VCA again, we are certified to get Taiwan approval. So basically we do our ECE approval with VCA. They make their approval report in a special format, which we then take and send to Taiwan and give them an extremely small amount of money, and then we get Taiwan approval. And I really mean that. It's like $50. It's the complete opposite of China. India, another country that has their own specifications, but again, they follow the ECE requirements. Testing must be witnessed by a agency from India. So there's two ways to do that. Either we need to bring their representative here, or we have to send our lamps to India. Kind of depends on the product and what we need to do and timing. So for example, in 2 weeks, we have VCA and India here for a series of products for a week to get all that testing done. It's kind of nice that way because we can do everything all at once. Just everyone here, they can all witness it together. But it is a lot of work to organize that and get everyone here and on the same schedule.
As we target more international business, such as India, are our lamps by standard just SAE and ECE approved, or can we make assumptions that our higher runners are India, Taiwan, all these different countries approved as well?
If our lamp is designed to meet ECE requirements, 99% sure it's going to meet Taiwan and India as well. It's just the approval process that historically we haven't gone through that we would need to go through if we wanted to sell our lamps there.
You cannot sell the lamp in India if it is not India approved. So it's got to be India certified, India homologated. All this kind of, sound very good and like kind of organized, but it's a big mess out there, guys, because really Europe is leading everything. They are making kind of, their regulations, and they have their own kind of, working committees, and everything is happening there. All the rest of the guys adapting or following these regulations. What does that mean? So basically, let's say someone in India has to take that regulation, which is very complicated, and translate that, okay? And put into a somewhat lingo and somewhat kind of, whatever it is, graphics that Indian local guys can understand that. And that is with China, that is with Hong Kong, whatever it is. So what is happening at this point of time, European standards are here and they are most updated. Now, there is a certain level of countries like China, Taiwan, or India, which are not in this level of revision. They will be, but they are not. And there is a kind of, following something which is kind of, taking and rewriting everything. It's the same, but rewriting. So basically, we have all ECE, that is all one things, but they're all on a different level of revision. So some technology, for example, could be accepted in ECE, but it still not get documentation kind of to be accepted in India. So you have to kind of work with them, you have to kind of talk with them, and kind of, so they realize that problem, but it's a pure administrative problem to kind of catch up with the newest regulations. And that's what we have, a different level of revisions for different countries.
And as Dragan said earlier, we're represented on a lot of these companies, so we're very up to date on what the regulations are and where they're going and what they're going to be. So sometimes when we've got a new product, we know, okay, we couldn't do this today, but we know 6 months from now the regulation's going to change and we're allowed to do that. So we're going to design that in now. So we're very up to date, but then if we have to take that lamp and send it to India, their regulation hasn't got there yet. So now we also have to sit down with them and explain to them, hey, this is where the ECE regulation is, and this is why our lamp does this, and we would like it to do that here too, and it's a bit of a negotiating process.
It's a very good sample of what we are kind of selling very nice at this point of our banking 7-inch round for motorcycle. That regulation is not yet adopted in India. So if you want to sell that in India, kind of, we got to go to the India and talk with those people and kind of explain them where are the regulations, what they do, how is that done, kind of, how is that measured, how it's supposed to be measured and everything that they can understand and accept it and give you that. if you just send them a lamp, they will send back and said, I don't know what to do with this lamp because I don't have that regulation yet. So they are far behind. They will have that in 2-3 years, but we don't want to wait. So because there is chances to sell that. There is a lot of things what we have to do.
And that goes into the decision of, do we send a lamp over there and let them test it, or do we need to bring them here so we can talk about it and make sure that everyone's has the same understanding?
When you kind of think about that, also in the information, they treat themselves as a prince on a red carpet. So you got to pay them kind of, business class from India here, okay? You got to treat them well, kind of pay all their expenses, and they're not hesitate to ask for a pocket money. Oh yeah, kind of, so I want to go in the mall for a shopping, I would like to have $500. They ask like that. Sure. Yeah, they treat themselves as a prince. Oh, you want approval, kind of, you got to treat me well. They just stamp you kind of knowing, just go, and you can do, you already pay all their expenses. So it's a little bit wild sometimes.
So, in general, if we're testing to a US specification, which would be FMVSS, SAE, ASABE, those are all self-certified. We do the testing here at Speaker and we're good to go. If it's going to another country, we generally need to have some other witness testing to get the approval that we need. And as we talked about, not everyone is up to date on technology and standards.
Just out of curiosity, is there like one big difference or two big differences you've noticed between FMVSS and ECE?
Yes, it is well, it's interesting story, and it'll take a little bit kind of, time, but since 1919, our two continents try to kind of, make what is the world harmonize regulations, and it never worked so far, so we want some things on some way, Europe wants some things on another way. So distinct kind of difference is really in geography and topography of our countries. We have a very big roads, so very open countries. So therefore, we don't care so much of the glare. We do have kind of glare regulations, but we don't care so much, kind of, because it's so much open, so much big, kind of, who cares that much? They have very small roads, very curvy roads, kind of, a lot of urban areas. You go from one city to another city for 15 minutes. There is no really, anytime when they come here to visit us, oh, look at that, how big it is. So really, so they care very much for a glare. So that is the major difference kind of between these two patterns. We don't care too much, they care very much for a glare. That kind of statement is driving different designs. Our kind of headlamps are just put on a car and go. Their headlamps are with the leveling motors, so which kind of exactly position the lamp what it is. They have a checking kind of their headlamps every single year. Today you just go over there, kind of, measure emissions, and you go with your car here in this country. They check everything, kind of, brakes, aiming of the lamp, kind of intensity of the lamp, everything, and every single year. So all it's based on that safety and the glare. That's the major difference. Okay. Now there is in that kind of lie down sub kind of differences like photometry points or whatever it is. We can go in those details, but it will take forever really. So if you're interested, we can talk some other time. But that is the major difference, kind of, safety and the glare between these two countries.
So just to illustrate his point, he said harmonization, that's something that they tried to do. So SAE and ECE got together and they made a harmonized fog lamp pattern. And that's what it's called, harmonized fog lamp. And it's not the same. It's really close, but not the same.
Now, this is the half. All that what we said now and talk about regulations and MVSS and EC and Japan and India and China and so on and so forth, that's the half of the story, guys. Another half of the story, what we're calling a COP, conformity of production. So they're all saying, okay, I'm going to certify you, that's fine, but now I'm going to come next year and check, are you performing to that what I certify you? That is the COP. And we have to, they come to audit us every year or every second year to certification to our lamps. Okay, and they have right to pick up the lamp, let's say, on the line and say, oh, China, for example, I want this lamp, go to photo lab and let's go measure. And if you don't, you have 6 months to kind of, correct that. If you don't correct that, they yank it out. And you have to go through all process together. So one half is the gain kind of, certificate. The other process is to maintain that certificate over life.
And some of that stuff we've avoided to some degree. They haven't been too vigilant about that up until recently. So Volkswagen and the diesel scandal took care of all of that. So everyone is a lot more stringent on what the regulations are and making sure that we are meeting all of those at all times. So the conformity of production is becoming a bigger issue, and more agencies are coming in to do those type of audits.
So in regards to the bullet point, not everybody is up to date on LEDs. You'd mentioned that the FMVSS 108 standard doesn't even mention LEDs. What is the classification that we use in order to design and build that specifies our LED lamps, and how does that relate to serviceability of a product in relation to replacing a LED bulb or lack thereof?
So, yeah, so as we said, FMVSS does not talk about LEDs because when it was originally written, they weren't there. So, fortunately, the way that the FMVSS defines certain type of lamps, we're able to fall under a category called integral beam headlamps. So all of our LED lamps are technically integral beam headlamps, which basically means that the source is integral to the lamp. There's no replaceable source. You can't take that out. And it's a solid unit.
That's how we get around, not we, everybody in this country. We are under non-replaceable bulb source. Now, it's a big debating going kind of, so they have that with the replaceable, MVSS calling exactly replaceable bulb source. Now, big kind of company like Osram, Philips, and some other, they want to make that small LED like type of the bulb and replace that. Well, the problem is how you put in MVSS. There is no lingo for it. And it's big kind of, debating how that to do it. So basically that you can replace the source. You can make a module which is kind of low beam and put into a somewhat housing to be replaceable. But now, how to certify that? What is that? How we can call that? Because MVSS saying replaceable bulb, it's not bulb, it's a replaceable LED. So they are kind of particular there. Also a question for that, what is the difference between MVSS and ECE? There's a big difference from our kind of perspective, also from optical. MVSS, whatever it's not written, you can do it. It's very interesting. Whatever it's not say, you can do it. ECE, you can do only what is written. It's a huge difference how you can manipulate one versus another, So there is so many things that we get away because it doesn't say, doesn't address MVSS, so therefore I can do it. When you read kind of EC, they're saying this and kind of, you cannot tell, oh, this didn't address. No, don't think about it. Only what is written, that's what you can do. That's a huge difference as well. Please.
I'm briefly going to mention a couple of things. Another set of acronyms that you may have heard or heard in the news recently and talk about what these things are. So one of them is the NHTSA NCAP 5-star safety program. And this is a new car assessment program, and it basically is about evaluating the safety of vehicles. There is currently a proposal. NHTSA updated their new car assessment program, and they have a proposal, and they put it out for public comment. And this new proposal includes information for vehicular lighting. And there's 3 elements to it. One of them is that your vehicle has automatic switching between high beam and low beam. So basically, when you're driving down the road and there's no one around, your car will automatically switch to high beam, and then when a car shows up, it automatically switches back to low. The second one is amber rear turn signals. In the United States, you could have amber rear turn signals or red. There's some study that show that amber is more conspicuous, so this program is pushing amber turn signals. Both of those things we don't really have anything to do with. The third one is a headlamp performance requirement. It talks about low beam performance, and it has some basically some further test points beyond what is required by FMVSS 108. Now, if you have a vehicle and you do all these things, you're going to get a better score for this 5-star rating. What it is for the low beam performance is a couple of points on a road that you test on your vehicle. So basically you measure a glare point over here on the left side of the road, and then 5 separate points on the right side of the road, and basically you need a little bit more of a punch than is required by FMVSS 108.
Just a quick kind of, reason. That is the NCAP where they're kind of, come up. Basically, these are the sensors. This is a static, so vehicle doesn't move. On a certain distance, they have a sensors, which is 1 meter like that, and they measure output of this light to those sensors. Well, why? Why that kind of suddenly, this kind of request? Why that activity? What has happened in the last couple, 3 years, there is a part kind of in Michigan University which is really studying safety and human response to the lighting in this country. And they submitted that data, name of that is AMTRI, and they submitted that data to the government in a certain kind of periods of 2-3 years. So in the last couple of 2-3 years, it was exponential increase of the hitting pedestrians by cars. It's kind of, somewhat 10 to 15% increase that pedestrians, especially in the dawn, not when it's night, especially when it's very early in the morning when it's light, kind of sun start to come up, or very kind of, late afternoon. Not at night, almost zero, which is interesting. People are alert kind of, when it's night, and when it's day, you can see it. But when it's that in between, the people getting tired or relaxed, or they're still not wake up, and they're hitting pedestrian. And that kind of, send that data, set government, we have to do something with that. And they started to kind of, build this NCAP. And that's why it's NCAP in this point of time.
So we do have at least one speaker product now that we have listed that meets these requirements. But just keep in mind, this is still a proposal. So we're meeting the proposed requirements, but what that actually ends up being at this point is a little unknown.
And which is driven by government, by data submitted from AMTRI Institute in Michigan.
There's also a Consumer Reports test that is very popular that talks about lighting. So what Consumer Reports has is a test track set up. This is also a static test. So you have your car parked here, and there's various points that they take measurements on and look at the performance of your low beam and high beam per their test. And they have their own values and what they determine is good or bad, and this is another form of testing headlight performance. Then there's a third one that's probably been in the news more recently, is the IIHS test, the Insurance Institute for Highway Safety. They have developed a test to evaluate headlamp performance. Their test is dynamic. So what they do is they drive a car down a road, and they have sensors at the end of the road, and they record the data as the car comes to those sensors. They also have GPS in the car, and they try to take out bumps in the road, and they have a very complicated system. But they do evaluations on a straight road and on left curves and right curves. And they have, these are all here, various curve sizes and straightaways. They measure at various points. Then they have a whole system of calculations on how far the light reaches and how much glare there is. And based on that, there's a formula that they go through, and then you calculate certain demerits. And the higher number of demerits you have, the worse your lamp is. The key feature here that is very important is that IIHS goes to a car dealership and buys a car. They do not do anything with the headlight aim. They buy the car, and they drive it, and they test it. So if you buy a car and your headlight aim is not very good, which as Dragan alluded to earlier, we don't pay a lot of attention to that in this country. So if you've got a poorly aimed headlight, you're going to do poorly here. And then they say, the Ford Escape has a terrible headlight, has a poor headlight. Well, maybe the headlight wasn't poor, maybe it wasn't aimed right. But how many people go out and aim their headlights when they buy a brand new car? So it's a complicated issue. So in addition to designing lights to meet laws and other standards, there's also these kind of consumer agencies that we may want to try to design our lamp to meet certain requirements here. Also, the complicated thing is that they're all different. So you can't just make one light and say, I'm going to get great scores on IIHS and Consumer Reports, because you probably won't. You probably have to pick one, and then maybe you won't do so well on the other because they look at various things.
This topic is kind of last 2 years topic on our SAE lighting committee. So by the way, next week, me and Brian going for 3 days for SAE lighting committee in Charleston. It's a whole day kind of debating about a lot of regulatory issue, but one day it's kind of just about this. Because they're all kind of different, but what is boiled down, what big OEMs kind of really saying that even if I'm here and I kind of score good, performance of that lamp could be very bad. Could be very bad. As you're kind of consumer, you can say, I don't like this light at all. Yet you're kind of rated good. So basically, it's a lot of happening in this point of time, but it's boiled down. You go, you buy the car, you spend kind of Mercedes $50,000, and it's every single one is rated bad. That's what big OEMs has a problem, So now I don't want to buy Mercedes because it's rated bad. Okay, it's nothing legal. It's just kind of something what they are saying. Hey, this is bad by our kind of things, and it's a big mess. We're still not kind of come through that, and I don't know if they were going to ever kind of change IIHS. Maybe not, kind of, we'll see. But it's a big debating going on in a kind of a world of SAE lighting engineers, how this is supposed to be. It's all about rating the lamp. And everybody has, God bless America, everybody has their own idea how to rate that. EC has their own way how to do it. And it's kind of done scientifically by calculations, and that's what's supposed to be. All this test is done by one kind of engineer who is not even lighting. He just kind of said, well, I think this is good. Well, how did you come up with those numbers? Well, it's all kind of also convoluted. Anyhow, there is a three kind of them. Consumer Report and IIHS is a little bit like this. Consumer Report prefer more spreaded light, don't care that much about the glare. These guys care about the glare. You can be beautiful, but if you have 1 point in the glare, you're above kind of immediately marginal at the best. Which is mean kind of, from our optical way, your cutoff line has to be that sharp that you never fail that. Well, when you do that, nobody likes sharp cutoff line. I don't want to go in that kind of, this is the elbow, what I'm seeing kind of here. So the cutoff line, sharp cutoff line would be this line, it's very sharp. So basically this is a very dark, this is a very bright. When you have that kind of situation, it's like you have a blanket in front of yourself. So when you drive, I saw the people, they're driving and trying to get under that because it's so much light here and so less light here, so that you perceive there is like a wall in front of you. When you go downhill, it's like you kind of, jumping in a well. You don't see anything. So that's why we kind of prefer that more to be kind of, very smooth and a lot of light above horizon. This one doesn't allow you. So anyhow, there is a 3 kind of rating systems. None of them is accepted by OEM. Now SAE finally formed a task force which is going to start to talk how we're rating the lamps. Okay? And also if public kind of accepted IIHS, what does that mean to the OEMs? They have to have a very complicated aiming system on the end of the line for each car to pass this. It's all about money. So we'll see where is that going to end up. For you, it's kind of just to know there is a 3 rating systems. None of them is accepted yet. It's a big discussion, and there is a 4th coming from SAE group as well.
First, let's just talk briefly about refraction or reflection, and then you can all be optics engineers. And I'm going to talk really briefly about light sources, because Brad will talk a lot about LEDs, and then we'll go through just some common optic elements that we use in our standard lamps here. When light goes through a material, it changes direction, and there's ways that physical equations that govern that, and that is basically what we deal with when we're designing optics. So light ray comes in, hits a material, here it says glass, it's going to bend, and then it bends when it goes out of that material as well. So this is the law and the equation that dictates where that ray is going to go, so we can calculate when a ray enters a certain surface, where is it going to go from there. We also look at a critical angle. So at some point, as the rays go through here, they start bending, but at some point, it's not going to bend anymore. In that case, it will stay within the material. So sometimes that internal reflection that occurs is something that we design. Sometimes it's a loss in our optical system. But either way, material bends, and at some point, it just stays inside.
There's a lot of mathematics, and after that, there is a kind of softwares and kind of, it's getting very complicated when it's all 3D and so on and so forth. But in your mind, kind of, so you've been fishing or see kind of, some documentary about the fishing in the morning, and the whole lake, it's like you can see the sun on that surface. So that's what is happening, really. So the sun is coming from air to different media density, hitting the bottom, okay? And let's say here it's hitting the bottom and start to reflect from a bottom, okay? And hitting on that critical angle and start to kind of, slide or kind of refracting again. That's why you see the sunlight on that surface, because it doesn't go out. As soon as that kind of, start to change direction, now is this happening, and you don't see anymore that kind of, sun on that surface. That's what is really. Or kind of, you don't see the sun, or and then you have a day, let's say kind of, afternoon. How? There is no sun, but you see the day. So the rays is hitting atmosphere and bounce back in your eyes, so you see the day.
Here's a couple of pictures of lasers going through some material, just to illustrate those points. So on the left, you see the laser at the bottom left going into the material. It's bending, and then it's bending back as it exits the material. In this case, we've got a couple things. So the laser is going into the material, internally reflecting again, and then going out. So these are the properties of the material that we can use to create the light pattern from our optical elements.
This is kind of, application, you all know, reflex. Front it's amber, rear it's red. That's exactly what's happening. The light is coming in, kind of, bouncing 3 times, bouncing up, and you're seeing that surface illuminated. That's the principle, exactly why it's reflex working.
I always put this picture in my presentation. Yeah. It's my favorite picture. So this is what you have to remember about light refracting. If you are a crazy harpoon man and you're trying to kill Nemo, where you see Nemo is not where he is, because the light bends when it goes through the surface of the water. So I just put one slide up to talk about light sources and the different light sources. Dragon kind of talked about some of this stuff before. So what I've got here is a picture of a halogen source with a coiled filament. We've got an HID source here, which is a plasma arc. And then we've got a LED array. All I wanted to point out here is that we do use different sources. Most of our new products are almost all LED at this point. But the distribution from the source and the light coming off from the source is different. So when we create optics based on different sources, where the light's coming from and how we direct it is different. So when you commonly see a LED bulb replacement aftermarket thing where they've got something that looks like a bulb and they just pasted a whole bunch of LEDs around it, why it doesn't work is because the sources are different. The light coming off those sources are different. So when we have a new lamp, how do we choose what type of optics to use in a product? So these are kind of the main things. First of all, specifications and regulations. If we've got a legal requirement to meet, we have to make sure that whatever optical system we choose is going to create a pattern that will meet those requirements. It has to fit in whatever package size we're looking to fit in, if that's customer requirement or our requirement or some standard product size. Styling today is very important. We talked about that a little bit before. When I started here 12 years ago, which is not that long ago, styling almost wasn't even part of it. It was, we designed a lamp to meet the requirements, and it fit a certain package, but how it looked wasn't that important. And today, it's almost the first thing. We need it to look a certain way, and then, oh yeah, it has to pass and do all these other things as well. So styling for lighting elements is definitely increased in importance. And of course, cost is also always a factor. If we need to do something low cost, we need to make sure that we're picking a very efficient optical system. If styling is really important and the most important thing, and a customer is willing to pay for that styling, then we can do other things to make it look really good, which might not be as efficient, but gives them what they really want.
There is one more thing kind of, which has become more and more important. It's electronics. So we have to kind of, pay attention to the electronics as well. We are becoming more electronic company. Our end product is light, but really what we are doing, we are dealing with electronics, especially now when it's coming intelligent and the kind of requirements with all that. So beside that, there is electronics, but this is a very difficult, most difficult part in our company to work with. Just one information for you. Once when you define kind of somewhat optics, it's everything starting from there. Then it's just kind of, upgrade until you see the product. But how products start, it's in this kind of, form. And there is a really hand kind of, people who can do this in our company. It's to do that, you cannot be only one skilled kind of person. You got to have multiple skills and knowledge kind of, to build start. Once when you have a core design established, then you build on it. Without core, it doesn't matter. Kind of, you don't have a product.
So now I'm going to very briefly go through some reflector optics, lens optics, and talk a little bit about projector systems. Just an example of what type of optics we use, what they look like, and kind of briefly what they do and why we would use them in certain situations. So this is a very basic representation of a parabolic reflector. So what does a reflector do? A reflector is going to take light from the source and bounce it in a different direction. So in this case, this red line would be our reflector. It has a focal point, so this is where our light source would be, and the rays that come off that light source hit the reflector and go straight out. And if it's a pure parabola, it's always going to go straight out. And what we do when we make a reflector design is we can adjust these surfaces to change the way the light is coming off and the direction that it's going. Another system, a reflector type that is used in projector lamps most often, is an elliptical system. So it's the same kind of idea. We've got a reflector over here, and this is the focal point. And in this case, the light's going to bounce off of there and all go through another focal point. So an ellipse has two focal points, and all the light goes through here. And then what we do is we put a lens out here that's focused on this image. So we're collecting the light, putting it at a point, and then making an image of that point out on the road. So in real basic terms, reflector optics bounce light around, and lens optics, we use refraction and internal reflection, and that's what we do when we design optics. We take light and we bend it or bounce it to get it to go where we want it to go. In really, really, really simple terms. This is just another picture, kind of we talked about before, refraction. As the light goes through material, it's going to bend as it goes through that surface. If we've got a relatively flat surface, you can see here the ray coming in and the ray going out are about the same angle. So if we've got a thin-walled, relatively flat outer lens, the ray going through this lens isn't going to be affected that much. If we've got something for some of our more heavily stylized automotive type lamps where the lens is at a really steep angle, now that has more of an effect on where the light rays are going, and we have to account for that. We get a little bit more internal reflection, that is loss, that we have to deal with. So the more stylized something is, the more it affects the light coming off a reflector or lens optic inside. So now I'm just going to go through real quick some basic shapes and lens optics that we use a lot of the time. An aspheric lens has a big long equation like this. So what an aspheric lens does is takes light from a source the source is spreading light in all directions, and it bends that light to go straight ahead. So a parabolic reflector does the same thing, bends all the light straight ahead. That's what an aspheric lens does as well.
Now you can manipulate this curve, which is calculated by polynomial, and you can spread it. You can do a lot of other things, but that's basically what does it do.
So the thing with aspheric lenses, they're usually pretty thick. This is a big surface here. So sometimes to break that up, we create a Fresnel lens. And what a Fresnel lens is basically that aspheric surface chopped into pieces and then pushed all together. So basically we're taking the aspheric lens that might be this thick and shrinking it down to something that's about this thick. So we can save on space. What happens is we've got little surfaces in between the optical surfaces, so we get more loss, but we save on space. We used to do this a lot. We don't do this as much anymore because it kind of looks like an old lamp from the 60s through the 90s. This shows some internal reflection, as I talked about before. So this is kind of a cross-section of a Fresnel lens here. We've got light rays coming from a source, and they're going to bend it straight. But at some point, it's not going to bend anymore. So then we create special optics to purposely bend and then reflect to get going in the right direction again. So as we said, sometimes we use the properties of internal reflection to our benefit, and sometimes we deal with it as a loss. A CPC optic CPC stands for compound parabolic concentrator. It's a very common optic you will see everywhere, and the reason is it's very optically efficient. So we have here on the side, we have an LED in here, and basically we're collecting about as much light from that LED and sending it out as is possible. That's why it's a very common thing. Everyone uses them because it works really well. So if we need a work lamp and we need it to be cheap and we need to get a lot of light out of it, this is generally the optical system we're going to use. The downside is everyone uses them, so our lamp would look like everyone else's. So that's where the cost versus styling and efficiency all kind of come together.
All the point, guys, kind of this optics is just to increase the efficiency of optical system. If you can put just LEDs without them, that's fine. Will work, so we're going to have a light, but you're going to have efficiency probably 30% or 20% or whatever it is. LED, as my palm kind of here, we're going to have this radiation, so 180, 360. Okay, so it's a ray going in every single kind of direction. This optics is kind of combination of the TIR. That's where people likes to use TIR because it's very kind of, so it's sound. It's really, what is happening, the LED is here. This half is working on TIR. This half is working on refraction. So basically the ray, if hitting here, refract hitting there, and then it's reflecting going there. if ray is hitting here, it's refracting going there. So everything what is coming in that LED, by theory, should go out. Now, we have a losses because this surface is not perfect, kind of, so it's good, but it's not perfect. There is some polishing kind of issue and so on and so forth. It doesn't matter. So, but this is the very efficient way. Doesn't look pretty, but it's very efficient way how to get there. And we cannot control. It's just taking that light, putting, let's say, in one bundle, and get it out. We cannot control very much here, but it's kind of, a lot of efficiency. We can spread it left and right, kind of, up and down, but we cannot make the immediately, well, why we don't 3 LEDs with CPCs make a low beam? Can't. I cannot control the light that good. From image which is that small, I get this big image. Don't know what to do with that anymore. For optical standpoint, we want to have the image as small as possible, as a point.
Flutes and pillows are optics that we use to basically spread the light. So we often use these in conjunction with some sort of collimating optic like a Fresnel or an A-sphere or a CPC optic. And basically, so we've got collimated light coming up in this case, and we hits those pillows and it spreads. So the curvature of these pillows allow us to spread light in varying degrees of how much ever we want to spread it. There's something called potato chip optics. That's when you sit in a hallway on the steps, very sad, because your optic design didn't work and you eat some potato chips. Not really. We use potato chip optics on a lot of our standard signalization products. It kind of looks like a potato chip, thus the name. And basically what it does is it collimates the light in one direction. So we bring in, if we got a big ball of light, we bring it in this way, but allow this direction to spread. So that's why on a lot of these lamps, we have vertical one, horizontal one, vertical one, horizontal one. So we create a spread this way, and then we create a spread this way, and it makes a very nice pattern for a signal lamp. Prismatic optics are like pillows, except they're a lot more complicated. So instead of just putting a radius to spread things, a prismatic optic is basically a very specific surface that we're putting in a place to get the light to go exactly where we want it to go. So it's a whole bunch of very, usually tiny, precisely placed optics. So the advantage of doing this in here is we don't have to collimate the light and then spread it. We can take whatever light's coming from the source and with one optical surface, bend it where we want it to go. Then we have D lenses, which we use in a lot of our headlights, which look like this, and from the side profile kind of look like a D. So that's where the very original name came from. And basically what these optics do and why we use them in our headlights is it makes a widespread uniform pattern. So it spreads out wide and kind of has a nice curve at the bottom, and that lends very well to creating the spread that we need for on-road lamps. Very briefly at the end here, I've got projector lamps. In this system behind here, we use an elliptical type reflector. That's going to go around the source. As we showed earlier, it's going to focus on the next point, and then we have a lens on the front that projects that image on the road. Projector lamps were pretty common with halogen and HID sources, which we never really got into making projector lamps with those sources. Now that we have LEDs, there's a trend, a desire to make a LED projector, which we are working on. So we use the same kind of concepts using LEDs as sources. It ends up being a little bit more complicated because of the LED sources, but those are still systems that we want to use and that people can then take out their old halogen projector lamp and replace it with a new LED projector lamp. I'm now going to turn it over to Brad to talk about LEDs.
Brad, it's our, for you guys, kind of advanced senior leader, manager, responsible for all kind of, advanced designs and kind of, LED in our company, managing the LED, evaluate the LEDs, measure them, kind of, and choose and accept as a standard kind of component. So he's going to kind of, give you a little bit overview about LEDs, how we choose, how we kind of pick LEDs, where we use them. We use them everywhere, and we'll go from there. Okay. Feel free to kind of ask the questions. We'll try not to kill you, not to go too much in kind of technical things, but you need to understand when we talk about LEDs what this really is.
So I'm going to briefly talk about LEDs. I do this a lot, so if there's any questions, please stop me and ask in the middle of this. And it's really somewhat brief. I'm going to go through what an LED is, characteristics that are important to us about the LED and binning. And then I'm going to talk, there's 2 slides on LED qualification. I'll kind of go through those quickly. And then how we choose LEDs for our products, what's important to us, and then who we buy LEDs from. And after that, I'm going to try to play a video for you on the manufacturing process that's involved with making LEDs, which I think is a pretty cool video from Osram. Just to give you a more technical background on the manufacturing, it does a nice job at a high level of going over that. What is an LED? So an LED is a semiconducting crystal that's been doped P&N, so it becomes a diode. And in between the P&N layers, an emission layer, that's where all the light comes from. That's where the electron recombination happens, so you have electroluminescence. So that's a big differentiator between the old Scott bulbs, which incandesce. In other words, you get something really, really hot, it gives off light in terms of radiation, trying to get rid of its heat. That's not what an LED does. An LED goes through this process of electron recombination in the diode that gives off light in that method rather than just getting really hot. LEDs, conversely, don't like heat. If they get hot, their efficacy or efficiency droops significantly because the crystalline structure of the LED, when it gets hot, isn't as perfect, and so its efficiency just starts to go down. And conversely, if it gets really, really cold, it also goes down. If there's like a kind of happy medium where the LED has a good output. So there's different types of semiconducting crystals that are inside LEDs. Primarily, we use Allen gap for red now. We used to use it for yellow as well, but more often than not, now we're using InGaN, which creates a blue and green color for yellow, because what you do is you use a phosphor converter for both white and yellow now, and it's a blue dye that's actually inside there. And the blue dye hits the phosphor, and the phosphor releases a yellow. And then in white LEDs, the yellow combines with the blue, and you get this nice white color. In amber, almost all the blue is filtered and or not filtered, but re-emitted from the phosphor as pure yellow light. So on a high level, those are what LEDs are. Most of our LEDs are all surface mount, modern type LEDs. In the old days, we used to be like a lot of T1 3/4 through hole type LEDs. We don't use any of those anymore. We're just mainly surface mount LEDs.
Quick note, kind of, you notice he used Allen gap, InGaN, what the heck he just said. So just explain what it is that kind of, if you can, Brad. These are the chemical elements which making the LEDs. Okay.
Yeah, so
Please.
in the video that I'll show you at the end, they'll show you kind of the process of how LEDs are made, but it's a semiconductor process where they have a reactor and they have a substrate, and the reactor basically under temperature and pressure conditions releases some other chemicals in there, and it reacts, and these chemicals build up on the semiconducting wafer. Allen gap is aluminum nitride gallium phosphate. So those are the chemicals in our red LEDs. In InGaN, it's indium, gallium, and nitrogen. Those are the crystalline structures. There's some other chemicals that are like small amounts here and there, and how the crystalline structures are created. That's the secret recipes that the LED makers use to really boost the efficiency, and that's their intellectual property. That's what their secret sauce is, and how they grow the crystals in those reactors. You'll see a little bit in the video on that, but that's basically what that is.
Do have one question.
Yes.
Obviously, Allen gap and InGaN are the two technologies that have been predominantly around for LEDs since about 1995. But with organic LEDs also coming out that are built with carbon structures, what sort of colors are available for those, and where's the efficiency of that technology in relation to the current standard Allen gap and InGaN technologies.
Okay. So organic LEDs or OLEDs are a completely different animal. The way colors are made with the organic carbon compounds are not necessarily with the different chemical lattice structures, but with the actual size and shape of the layering of the hydrocarbon layers. So that's a completely different
They
animal.
can control that band gap, basically.
Yes,
Okay.
in a different way, not with chemical means, but by dimensional means,
Oh, wow.
much like other electroluminescent materials that they've been playing with. Where they are efficiency-wise, they are not quite as efficient as an InGaN. For instance, the efficiency of a blue InGaN die nowadays is more than 50% almost, which is, to me, is amazing. It's holy cow. You get at least 50% of the energy that you put into an LED out as light. That's pretty awesome. OLEDs are almost there, but not quite. The other difficulty with OLEDs is that they are hydrocarbon based, and if they're penetrated by oxygen molecules, or in general water, they tend to degrade rapidly. So encapsulation with OLEDs is the huge issue. The other thing with OLEDs is they don't hold a lot of current density, not like these. These can hold a ton of current density, and therefore the luminance of OLEDs is way lower, orders of magnitudes lower, like 100 times less almost than this. So that's, when you use an OLED, typically you're not using a lot of optics with it because it's a very big, wide source. So you can't really direct it as well.
And the color consistency due to temperature.
Yeah,
Over time, it's kind of, shifting the colors,
So for
yeah.
signalization, that's the problem.
Yeah, somewhat problem, yeah.
Yeah. So, yeah, clearly we don't use any OLEDs at speaker yet. We're just using regular semiconductor LEDs. Characteristics within LEDs that are important to us are the color, obviously, of LEDs, flux, which is the light output, so luminous flux, and forward voltage. And what LED manufacturers do, just like any manufacturing process, there's tolerances involved. They can't make an LED that's going to put out exactly 10.0000 lumens. It doesn't happen, right? So there's a range. And just like the flux output, there's range on color, and there's range on the forward voltage of the LED. So and you'll see again a little bit of this in the video that I'll play, but when the LED is manufactured, at various points it's characterized by the manufacturer for these various things. They'll measure the flux of the dye, they'll measure the color, they'll measure the forward voltage. And then they put it into these groups called bins or ranks. And as an example, here are some color bins from Osram. We might say, we can accept, for this particular LED, we will accept this range of color in the pink there. So that means you might end up with an LED that's in this bin or in this bin. And so there's going to be a variation in color. There's going to be a variation in light output. Here are some flux bins, for instance. So if I were to buy all of these flux bin in one part, this part would go from 112 lumens all the way up to 164 lumens. Brian and I, when we do an optical design, we have to take all those things into consideration and try to determine, are we going to be legal at all these different points? And is it going to be acceptable to the customer at all these different points, both from a color and a flux standpoint? There's also variation within the forward voltage drop across the LED when we drive it. So, for instance, these are all the forward voltage groups for this LED. It goes from 2.8 volts all the way to 3.25. We don't limit the binning as far as voltage because that would be very expensive and be another thing to take away. So we typically accept it all, but the electrical engineers, when they're designing the circuitry, they have to account for the min and max voltage that the LED has. So when we choose an LED, the first thing we do is we don't always trust the manufacturer of the LED because different manufacturers have different test methods. We like to get samples ourselves. We like to mount them ourselves with our SMT processes. And then we use our photo lab to qualify the LED by taking flux measurements, sometimes color measurements, and the forward voltage measurements. And then I put it into kind of a little mathematical model I have to compare it to other LEDs we've measured and understand what its worth is. And then I tell the manufacturer, I'm willing to pay this for that LED, and hopefully get that price or lower. So in addition to that, sometimes we'll do halt testing occasionally on some LEDs just to understand the failure mode. LEDs are very hard to kill, though. I want to be clear about that. Typically, the thing in our lamps that's going to die is very rarely the LED itself. The only thing that really kills LEDs is a ton of heat, and I mean a ton. And typically, other components in the lamp will be dead first, like the plastics or other electronic components. So LEDs are really tough. Like I said, they're crystalline materials. And then the vendors put it through pretty severe testing too, with either an automotive qualification like AEC Q101 or a lighting qualification, which includes like LM80 data and testing to various JEDEC specs. So when we go to choose an LED, we're looking at optical criteria, the flux range and the efficacy, image size and shape and consistency, the viewing angle. In other words, if there's a dome or a lens on top of the LED, how the light is coming out of that LED, and then the color range as well. We're looking at how well the LED responds to heat and how low the thermal resistance is. And then looking at the limits that the manufacturer has out there for the thermals and how the color changes with thermals. And then also we want to make sure that we're meeting our manufacturing requirements as far as being SMT mountable, and then looking at all the other solder pad configurations and stuff and make sure we can work with it. There's also commercial criteria. Obviously, we want to get the most LED for our dollar. And we don't have a disrupted distribution channel either. So we want to make sure we can maintain a solid flow of LEDs for our products. And then the quality criteria, which is partially based on vendor history, but then also the actual qualification plan that the vendors put it through. Our main LED vendors right now, Nichia, Osram, Philips, and Cree. Some of them, like Nichia, Osram, and Philips, they have both automotive qualified LEDs and then lighting qualified LEDs. Typically, with an automotive qualified LED, you're going to have a little higher cost because of the qualification program it has to go through. It has a little bit higher thermal robustness, perhaps. And then they try to protect the availability, but it's not completely protected. And then there's lighting qualification programs. The lighting qualification moves quicker typically, so you get more cutting edge technology. The efficacy is typically higher, and therefore sometimes for like work lamps, you'll get a better value on the LED. But on the other side, they can discontinue those LEDs at any time because they move fast. So the LED vendor can come out and say, in 6 months, you can't buy this LED anymore, and then we have to scramble. So those are risks we have to face.
When you change out the LEDs, like what effect is that having on the lamp such that, I mean, you would have to recertify the lamp? Or does that change?
It depends.
Would visually change
It depends
properties?
how drastic the change is. If it's a simple dye revision, say hypothetically we're moving from a Nichia 170B to a Nichia 170C, we might be able to get away without recertifying, and we might be able to basically just change it almost in sightline and just keep going because there's no requalification that has to be done in SMT or anything like that in some cases. In other cases, if there isn't a direct replacement that is fit, form, function the same, it's a huge deal because then we basically have to redesign the circuit board for the LED. We have to make sure that optically we're okay. And then we do have to re-homologate everything, recertify everything. Every certification that lamp went through, we basically have to repeat.
It's very dependent. It's very dependent of the customer, market, and what you do with it. Even if it is, we try to get away as much as we can. That's the honest answer. So in the homologation documents, there is a code of LED. So if that LED is very kind of, precise, specify, then by the book, you have to re-homologate it.
Yeah.
But we try not to put that very hard. We say Osram white LED and then we swap the LED and we don't homologate it, okay? So, and then when we do that, if it is a China and we change board revision level, because China wants to kind of define main component of the lamp, okay? So when you do the revision level, you're gonna have different revision level, and after that you have to re-homologate again with the China. It depends. We try to kind of minimize that, but sometimes we get away, sometimes we don't.
And it's always a struggle sometimes too, specifying LEDs for us on the front end, right? We want to be on the latest cutting edge. Well, we want to make sure we're not going to disrupt the launch of a product because we're going with the latest cutting edge LED. Because it's always like, okay, do I go with this brand new thing that I think is going to come out in April, or do I wait and go with something I know is steady and stable now? Because in a year it could be like, oh, I'm behind the curve now. And to change the product, it's a pain sometimes. So it's a struggle. And LEDs change often. You know, the technology keeps improving. So again, the LEDs we use right now come from Nichia, Osram, former Philips. It's just Lumileds now. Cree, and all of those companies are industry leaders. They pump tons of money into their R&D as far as their technology. They all have license sharing agreements amongst themselves, but they're developing new IP all the time. We get regular process and technology roadmaps from them, and they all have pretty decent distribution channels in place. Right now, Nichia is by far the best at the moment in terms of distribution. I'm sorry this got all messed up here, I'm not sure why. But other LED vendors, I mean, if you can think of an LED manufacturer, we've probably talked to them at some point. We're particularly still, we keep playing with the Korean manufacturers like Seoul Semiconductor, LG Innotek, Samsung. I think they have some compelling products. But then there's a ton of other guys that are out there that we've talked with.
So these are the LEDs, guys, kind of, there is another kind of, sources before he starts the movie.